here, and I'm going to talk about Vide and Vectrex. Today or yesterday I got a letter from a fellow Vectrexian, and he programs in C, and he asked me about optimizations, if I could help him or if I had some tips. This is the email I got. I'm just going to show it to you and the questions he asked, because I realized that most of the questions I will not answer actually, but only give some tips about optimization, and this is what this video is about. So he asks some questions. He's programming in C, you will see that later. I can see that there is an option to export vector lists as source code. So as source code, yes, you can export vector lists in source code, but it's always assembler. I do not generate C source code for vector lists, and yeah, that probably doesn't make much sense, and I haven't programmed an algorithm for that. However, I cannot click the moves and draw buttons in the export dialog. In Vecchi, yes, you cannot export all vector lists even in source code. I have not actually programmed all options that there are. The vector lists must have a special, must be special in the way that they are connected, or specific patterns must be matched, and so on. It's described in the help system. I don't know exactly what your problem with that vector list now really is. I have to would have to look at it directly, and then I could probably tell. But I will look at the vector list you mentioned here anyway later, and I will optimize it, but without generating source code. Blah 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 blah. However, I assume I can mix C and assembler in Vide. For now, I cannot even export the source code. Yeah, the source code, that's what I mentioned above. And yes, you can mix C and assembler in Vide. There are two options. You can use the asm command in C that in GCC features, or you can actually include pre-compiled object files, but that is pretty enhanced. I also described that in the help manual. I'm not going into that with this help video either. So, but now, if you have any other tips on how to optimize the drawing, I would appreciate it also. Yes, that's what I'm going to do. This video I'm going to show some optimizations that I came up with, and yes, show it to you and to all other people who might watch. The game I'm talking about, I'm going to show it to you. I recorded video before just showing the game so that you may look at it, and the easiest for now is, since I'm recording a screen anyway, I just play it. Spidex.move. Spidex, that is the game. It's loosely based on Black Widow. This is the spidery thing. This is the web that is mentioned in the email, and the game already plays very nice. It's a fine game. This is the web. It's well, Black Widow is a little bit like Robotron on a featuring on a web. This is also this is a spider which can shoot in all directions. You can even use two joysticks, one to move and one to fire. Here I played with just one joystick. It's also an option. The game is not finished. I think it features by now 3 different levels, and a couple of enemies, and food, and so on. Yeah, that was a short video I recorded. The game actually is, or the source code is publicly available. The programmer goes under a name Phobos, and under GitHub the sources are checked in. And actually, since I already yesterday did some optimizations. The source code that is available on the web has already the things that I did included here. You see incorporated optimization changes. Thank you to Malban. But anyway, I'm going to show you what I did, or I think I will show you. So let's start. This is the export from the GitHub you just saw, and I'm going to run it just as it was yesterday when I received the source. Or when I checked out the source. Here you see the spider. You can play, and it looks rather well already in Vide. But if you add Tracky, you see that the game is at the moment quite slow. Here it goes up to 50,000. This is 53,000. That is nearly 25 Hertz, and optimum would be this green line over here, 50 Hertz. So what we are going to do is try to enhance the source code or the game so that it is below 30,000 cycles, and actually we are going to do that. Not under all circumstances, but there are some tips left with which one most probably can achieve that also. The entire source is written in C. These are all sources here. It includes one or two libraries, I think, that I wrote for the IEFX player, but nonetheless the complete source code is in C. Well, the first thing I did, and that already was a huge step for a faster game, was to look at the project. If you right click here on the root of the tree in the in Vide, you have the menu item project properties, and I looked at that. And Phobos kept the default options intact. He didn't change anything, and the default options are without optimizations. And the GCC C compiler actually has some pretty neat optimizations. -03 entered here to the C flags is sometimes the best optimization, sometimes O2 is the best. You have to look it up what the difference actually is. Sometimes the source code may become too large because it does loop unrolling, or it structures the source code differently, or. So you have to try. I always try O3 first, and then O2, and I look at the size of the source code, and then I decide which options I keep. Also, what I always do is C peepholing. I enable that because C compiler, under some circumstances, produces wrong source code. That is so because GCC for the microprocessor of the Vectrex is not perfect. Actually, it has some bugs, and the bugs that I discovered, I correct within Vide. This, if you enable this checkbox, Vide explores the source code generated and looks for bugs. And if it discovers bugs, it removes them, but only, well, bugs that I discovered before. And also, if obviously redundant code is generated, it's also removed. So it's a little bit better if I didn't make any mistakes or included bugs of my own, if you keep that switched on. Then there's another option, C RAM inlined or not inlined. This you have to try. It's different for each C program that you write. Sometimes the inline version is faster, and sometimes the function version is faster. You just have to try it. There's not a really big difference anyway. So, but I chose O3, press OK. Now the game runs at max 51,000 cycles. I compile it again, and press the reset button now, and let's look how much faster we get. You see it already here. It's, well, actually nearly 20,000 cycles faster by just enabling the O3 option. So there you see the GCC compiler can optimize its source code pretty well. This does not mean it's perfect, and it doesn't mean it can go any faster, but it's actually quite good. Excuse me. This video program I use does not have a pause button, so if I have to cough, I just have to cough, and you have to bear with me. So now, actually, this is the start of the game. There is no shot displayed. There are only two other enemies. The web is drawn and the score. So there's not really much going on in the game yet, and yet it still is drawn in 31,000 cycles. So it's already above 50 Hertz. And we will try to enhance it so far that it goes below that, so the screen does not wobble. Next step is to look what Phobos did. As you can see in the email, he actually suspected the web. Where is it? The vector list is stored in the directory the web. Blah, blah, blah. One moment. The game is very slow due to a large spider web covering most of the screen. Well, let's look at that. How much of these cycles, how many of these cycles actually are used for the web. So by now I know the source code a little bit, because yesterday I already looked at it, and here's the main file, and the main file is always a good start to look at. And I scroll down all the way, and I happen to know that this function here draws the complete web. Let's just inspect that function to see how fast that or how many cycles it uses. Therefore, I will use Dizzy. Perhaps this is. Did I enable debugging? I don't know. Project keep to see debugging. I'm not sure. This C debugging is a little bit snippy. Sometimes it works, sometimes it doesn't. It doesn't do anything wrong, but sometimes it just does not work. So this time it probably does. Here it jumped to the debug, and you see here this is a draw sync line that is that corresponds to this draw sync. We look at the cycles, how much it costs. I set the cycle count to 0, and this is the actual subroutine function, and this above here sets up all the parameters. So I step over the function. Now the web is drawn for one go, and I see the web is drawn in 12,555 cycles. Yes, that is pretty huge, a large amount of cycles. On the other hand, it is nearly, it's quite a lot that is drawn. We should look again to get it a little bit faster, but as you see, the web is drawn from the outer edges, very large vectors. I don't know how many vectors we can look at that now. It is a huge list, and we can expect it to use many cycles. We will try to enhance it, but this is a figure that we now know. It's about 12,500 cycles only for the web. So, since the source code is quite well structured, and there are files, different files for all the things that are done, we can easily identify where the web is defined. And it is defined in a file called web.c. Here you see the this is the actual vector list for the web. It's quite huge. Let's look. This is line 10 to line 60. It's about 55 or so vectors. It's quite a huge list, and it is one list. And let's go back. The draw sync lists. These are actually scale factors. This is a scale factor for the move, and this is a scale factor for the vectors that are actually drawn. It's both $80. It's 128. Yeah, well, the scale actually is a timer T1 that is used by Vectrex to draw vectors, and it's if you go for a faster game, you always should look at the scale factor of your vectors to get it as small as possible. Well, if you go from the middle of the Vectrex screen to the outer edges, you usually must use from the middle to the outer edges about $80. That's the time. Well, you cannot reduce the time. If you just go from the middle to I don't know, from the middle to the middle of the you know what I mean, to here, then you could do that with a scale factor of I don't know, $40. But to draw to the edges from the middle, you must use a scale of about 80 at least. If you draw a diagonal from one corner to the diagonal corner, you will need twice as much, probably about FF, so 255 cycles or something like that. That's approximation. The vectors are drawn with two factors always in mind. The strength of the vector, which is actually the voltage that is input into the integrators, and the time for which this voltage is applied to the electronic. So these two factors, the strength and the scale, if they result in the same product, the vector has the same length. So a vector with a strength of 10 and a scale of 50 is, if you want to call it in that way, will be 500 pixel in quotes long. If you do a vector with a scale of 10 and a strength of 50, it's also 500 pixel in quotes long. And if you want to draw fast, well, then you go for the least scale. I think I probably explained that 100 times before, but and I'm stuttering here a little bit and I can't pause the video, so well, just bear with me. Anyway, this is one huge vector list, and in one vector list all vectors are usually drawn with the same scale. So what you see here are 55 vectors which are all drawn with a scale of 80, and that is usually bad. 55 vectors, let's see, here's a okay, 55 vectors with a scale of 128. Just the pure drawing of the vectors, you do not position them, you do not switch anything on or off or whatever. Just the pure drawing of the light are over 7,000 cycles with a scale of 80. So if you use a scale of 80, this thing will never be really performant. Full stop. So the thing that I actually did is I split this vector list up in different parts. We go to Vecchi, and I will show you what I did. I take this vector list. I didn't check out the XML files, so I use Vecchi to import this thing. Becky cannot import synced lists. That's well, stupid of me, but it is so. Therefore, I have to correct this vector list so that Becky can actually understand it. For that, I remove all the syncs. And I think then I can just, yes, use without the sync. It's the same syntax as a draw VLP list. So this is actually the web. I can edit now in Becky. So what I actually did was switch this one huge vector list to 1, 2, 3, 4, 5 separate vector lists. I did that the following way. First, I save the complete vector list. Perhaps I need it later. Add current. So within the animation or scenario, this vector list is now saved. And now I, oops, wrong mode, point, vector. I start in the middle. I take these vectors, delete not selected. This is the innermost web circle. I optimize this with easy through all and save it. Then I take it back and delete selected. Now I do that with all the other vectors, and so I delete not selected, easy to all, add current, and so on. I do this with the whole thing, and when I'm finished, I'm sorry, I can't pause, so I can't hold, so you have to see it all. Delete selected, do that with these ones here. Sometimes it's better, easier to just select the vectors, delete not selected, easy to all, add current, undo, oops, undo, delete, selected, and the last ones here. Not that one, doesn't matter. Delete not selected, easy to all, add current, take back. So delete not selected. Damn. Sorry, I'm just being a little bit stupid here, it seems. Delete selected, delete selected, delete selected. So I think these are the rests. Is it true? Yes, add current. Now, you can't take this step back. Okay, just believe me. I accidentally deleted the list here. Just believe me. If you split these up, you can draw them separately with different scale factors. I can show it to you what I thought I could show you. Damn, what's wrong here? Which one is that? Spidex. Yes. This is what I did before. This is the innermost web. Then the next web, these are the spikes, so to say, of the web wheel, and these are the two last circles. And here you can see that I built different lists, each with a so-called blow-up factor. The innermost web actually has very small strengths, and I enhance the strength with a factor. If you look at these values, the largest value is $B. $B is 11, and we always want to go near 128. So actually I could have taken 11, but 10 is such a nice number. So I used the blow-up factor of 10. Now this 11 is actually 110. And this is the largest strength now of these vectors, and I blew up all strengths by 10, and at the same time I can reduce the scale factor, divide the scale factor also by 10, and the size of the vector is nearly identical, or of the drawn web. So where's my calculator? Anyway, it doesn't matter. Just believe me. In the where's the main? In the main routine, the former draw sync list of the one web is now realized with 5 different draw sync lists with different scale factors. This is a web 1, which I just shown you, and it has a divider of 10. The web 2 has a divider of 3. The web 3 has a positioning divider, in this case by 8, and web 4 a divider by 2, and the outermost circle, yeah, well, these are large vectors. I left them at the scale factor of 80. I did this same procedure with most of the enemies encountered in the, well, with most sprites, if you want to call them that, of the game. All sprites are defined in separate C files. Here you see the B, and right from the first look of it, you see these are really low numbers. The largest number here is 13. And what I also did is I exploded this vector list also by a multiplier of 10. I show you the here. I defined an amplifier multiplier by 10, and actually multiplied each values. You can see them, well, near each other. These are the same values: 1, 2, minus 10, minus 1, 4, 10. These are the exact same values. I just exploded them, and at the same time I reduced the scale factor used for these enemies. Where was it? Is it in enemies? Yes, here in the C file. The B's are defined as an object. This is actually a structure which initializes the objects, the enemies. And here you see the original scale factor was 40, which is half of 80, but 40 still is $40 is still a scale factor of 64, which is still huge. Anyway, 10 times as huge as divided by 10. Here I see the enemy. Here you see I just wrote here divide by 10 and multiply by 10. And this I've done for nearly all objects. There was one catch, as I showed you before. The B, or some of the others, has one number, the 13 in this case, which multiplied by 10 goes over 127. So actually this goes out of bounds of our 8-bit border. Multiplied by 10 is 130, and that would actually be minus 126 or 25 or something like that. So the whole structure would be destroyed. Luckily, this is a move vector. What I did actually is I made two moves, one with 7, one with 6. And the sum of both is again 13. And with this trick I can still use a scale factor of 10, because 7 and 6 can be multiplied by 10. And the whole B does look exactly the same, because this is just a move vector. So if I just move from, say, here to here, invisible, and then invisible from here to here, it's the same as I move from here to here. That can often be done. With move vectors it can always be done, because you can go around corners or whatever, you don't draw the vectors, it's just the end result that counts. If it's a draw vector, then you have to look if you can actually draw the same vector with two vectors. But luckily all these drawings, all these large vectors I encountered in this files I checked, always the large numbers were were move vectors. So this I did a couple of times, not often, and this is a list of how many vectors? 26 vectors. Well, if you have to do it often, then say 5 or 6 times within 20 vectors, then you should think about another amplifier, not 10 or something lower that actually 13 can use. So scale factor or amplifier of 8 would have sufficed for this one. It's, well, it's fine-tuning. Yes. As I said, I did this with all enemies. There's a bee here, there's a bug here, and there is a fly, and food, and a mine, and the spider itself, and a sparrow, and star. And there are quite a number of actual sprites that I had to change. Well, it was a search and replace actually, and figuring out the correct number, and changing the scale and the appropriate places in the source code. Then, as you might have seen, these vector lists were generated with Vide, and they are synced lists. Some time ago I did this draw sync list for C and published it on my pages, and Phobos used it, which I'm very happy about. Where is it? Draw. It's called draw. There it is. This is a draw sync list which I published, and it's actually quite good. It's actually more performant than the assembler version. Actually, I don't know why, and I haven't optimized the assembler version lately, but this thing is actually faster than the assembler version that I programmed. So it's a quite good list, good function to use actually, I think, to draw fast. But anyway, it is some time ago, and Vide was not enhanced at the time as it is now, and the C compiler was not as enhanced, so this function could also be enhanced. As you can see, all these names are actually the via names, but well, I don't know how I can easily describe it without going too much into the assembler. I'm just going to tell you, these names here are translated to assembler code using extended addressing, but you can also use direct addressing. Direct addressing is always one cycle faster and one byte shorter. So for each of these variable names, so to say. So if we can use direct addressing within these function, which actually does a drawing, it's a quite huge enhancement. And the only thing you have to do today, after Professor Per Johansen optimized the C compiler, is actually to write a direct page underscore in front of it, and then direct addressing is used. This is a feature also explained in the help file and on my web pages, but if you just do a copy and paste and I do not enhance my own website, well, then you don't have it. This is also what I did while optimizing. Here is the draw function. I open it. Here you see there's always a dp underscore in front of it. And this actually is also a huge cycle saver. Well, there's another thing I did. If you watch closely in the draw C file, here there's only one function, draw synced list C. If you looked at the main file, then you in the enhanced main file, then you see here that I use other draw synced list functions. These are slightly optimized. This is I don't know if it's actually worth it, but it is an enhancement. For synced lists, you can always enter a coordinate from which it is drawn. So if a synced list, if I open this here, if you look at it, if I want to draw a sprite here, then the first coordinates passed to the draw synced list is always this coordinate, and if a syncing actually happens, it resets to 0, goes back there and continues to draw. But this web is actually a special case because it is drawn from point 0. From point 0 you do not need a move. So this NM draw synced list is a no move draw synced list. This actually the routine is one move shorter than the other draw synced list, and one move with a scale of 80 is another 128 cycles at least. It's more, probably about 200 cycles or so, wasted for just nothing, because if you enter a coordinate of 0, 0, then for the scale of 80 it moves from 0 to 0, which is, well, nonsense. So I actually built another function, no move, with actually a part of the function just deleted and renamed it and used it, and that way I saved again another couple of cycles. Then you might see there's a no move 1 here. This is again a special case. All these things could be done in a couple of minutes. This is because I did it. These diagonal lines in the web, they are drawn more or less from the center, and the actual list looks like this. It's always one move and one draw, one move, one draw, one move, one draw. So if you want to go, this is a middle point, one move to this starting point, one draw, reset to 0, one move, one draw, reset to 0, one move, one draw, reset to 0, and so on. This is exactly what's here. And the specialty about it, it's a no move vector list. It starts always from 0, but does a move from 0 first to the first vector. And this move is special in the way that it is very short. It's a very short move from the middle. So this new function here has a draw scale of 80. The diagonal lines are drawn with a scale factor of 80. But the move from here to the start of drawing, that is actually, the scale of that is actually defined here. It's a scale of 9. So it's a really small scale. And again, this small scale, 1, 2, 3, 4, 5, 6, 7, 7 times 110, about 1,000 cycles just saved with this special function. And it's not, well, it's not so big. The complete binary by now with all these functions is about 17K. Well, it's huge in compared to original Vectrex cartridges, but well, nowadays only levels are missing within this game. Otherwise, it's nearly complete. So it will easily fit within 32K. Well, yes, I think that is actually all the optimization, apart from really small stuff which I can't remember, that I did. So let us look. Is this the optimized version? No, this is the non-optimized version. And somewhere where I just had it, didn't I? Did I close it? No, this one. This is the optimized version. Let's look if I also have the properties right here. Yes, it's 03. So let's run that. The optimizations I did, well, I had to look at the source code and learn a little bit, but I did it in about, I don't know, 2 hours or something like that. So here you see the game when we started refreshed in about 51,000 cycles or 52,000 cycles. After the 03 setting, it refreshed in about 31,000 cycles. And with this optimized web list, it refreshes now within, well, about 25,000 cycles. It looks pretty good. But it can still be enhanced. If I play a little bit, or just if I shoot, you can see when I shoot, there are 3 shots in the air. And only with the shots without any other enemies, it already reaches about above 50 Hertz. It goes up to 31,000 cycles. I'm playing a little bit for a few more enemies, and you will see it is still a little bit slow, and I'm going to talk about a little bit about that later. So there's the spider enemy coming up. So you see the slowest we had was 38,000. Well, most original Vectrex games refresh far less often. I don't know, they really go up to 45, 50,000 cycles or something like that. So even if it stayed that way, it would still be a good and fast game. But I'm always a perfectionist. I also would like to get this one faster, and it probably can be done. The thing I'm thinking about now is what takes so much cycles away is, I think, collision detection. I looked a little bit at the sources, and somewhere, where is it? Here, these interactions. Interaction enemy player. Within these and interaction food, this is where the collision detection is done. Player also means shots in this special case, and it looks if the player collides with an enemy sprite. Here it does a collision detection if a player collides with food, and within these interaction enemies player also the shots are tested if the shots hit any enemy object. One moment, where is it? I think it's in player. Draw player. Interaction enemy players. Here you see it. Here the player, if the player is active, so it's not dead, then all enemies are looked at in a loop. These num enemies are actually all enemies. Here you can see this is max enemies. And for each enemy, each bullet is also checked. And the check is done with this hit object enemy. Where is this thing? The hit object, was it in here? This is a actual hit object function, which is not too bad. I don't say that. This is pretty fast, even if it looks a little bit involved. It's a pretty good collision detection. But there's one player. There are 3 bullets, I think, and 5 enemies. Is it 5? No, there are 3 enemies max, food 5 max, and 3 bullets max. So these are for each enemy a collision detection with a bullet, which are 9 collision detections. Max food is 5 collision detections. Then enemies with the players, again 3. Then we are by way over 20 collision detections when worst comes to worst. And this A must be optimized and B can be optimized. I did some testing, and the collision detections take, well, I think 6,000 or 7,000 cycles. This is huge. Within Vector Blade, the game I'm currently writing, there are about, I don't know, 20 enemies and 10 shots. 10 player shots, about 20 enemies and about 15 player shots, and all collision detection is done, I think, in, don't know, 2,000 cycles. Well, that is pure assembler, and I whacked my brains out to actually achieve that. I think one thing that can actually be done is, for each round, all collisions are detected now. Each game round is about 1/50th of a second, and I don't think it is necessary actually to check each enemy with each bullet each round. One could divide this check up in, I don't know, only 1 round for each enemy each round or something like that, or perhaps one could divide the screen in an upper and a lower half and check, since most shots are always done in one direction, because one could say only enemies that have a coordinate in the upper half are checked or something like that. And that, in addition to not checking always all enemies, I think it can be optimized. And well, this is more an algorithmic optimization. What I did here was more Vectrex technical optimization, if I want to call it that. But I'm fairly certain the whole game, even in C, can be done in under 30,000 cycles. The game, as of now, is not yet complete. It's 3 levels. But yeah, I think it's very promising, and I'm looking forward to the finished product, and I hope Phobos actually finishes it. The name Phobos actually was not all that new to me, because on my C page I frequently look in on the web if I find something new in Vectrex, and there were C-related projects. When I find them, I link to from my Vectrex C page, and there already was a start of a Tempest clone by Phobos in May last year. It's also a GitHub repository, and I looked at it, and well, that was far from finished, and it looks like he didn't do anything on it for well 8 months, I think. But that was where the name Phobos rang some bell within me. And within the same repository now is the Spidex, the Black Widow clone, which is already quite enhanced, and well, you just saw it. Anyway, that's all for now. I think I stuttered a little bit. Don't know if it was a really great video. And the faux pas with Becky with deleting all this stuff really, well, but I didn't want to do it again. It would have been boring for you too. So I hope I could help anyway in some way, and I wish you a good night. Goodbye.